When engineers test a new synthetic material, they often need to know exactly how it reacts to environmental factors. For instance, they need to map the relationship between the ambient relative humidity and the actual moisture content absorbed by the material. Looking at this scatter plot, the raw data appears scattered and messy, but to predict how the material will behave outside the test chamber, engineers calculate a line of best fit. They model the entire dataset with a single straight line. Visually, that line is a single object extending across a grid. Mathematically, it is an infinite, continuous set of coordinate points stretching in both directions. To actually utilize that infinite line in a software system, we cannot rely on a drawing. We have to translate the visual geometry of that specific trajectory into an exact algebraic equation. This process of converting infinite visual space into a singular, computable formula is the strict mathematical foundation that makes data science and predictive engineering possible. To see how that translation works, we are going to build a universal mathematical model of a straight line, starting from first principles. First, we have to isolate the single invariant property that locks any line's trajectory in place, its slope. Once we define the slope, we can use it to derive the standard algebraic equations that represent lines on a graph. Finally, we will prove how purely visual concepts, like two lines running perfectly parallel or intersecting at exactly 90 degrees, are dictated entirely by algebraic constraints. Mastering coordinate geometry requires successfully mapping the exact mechanisms by which algebra dictates the rules of physical space. On this Cartesian plane, we define a line's slope, m, as its constant rate of change. It acts as a rigid ratio, the vertical change divided by the horizontal change between any 2 points. Mathematically, this is y2 minus y1 over x2 minus x1. Because a straight line's rate of change is perfectly constant, the order in which you select those 2 points is immaterial. You will always calculate the exact same ratio. This split screen shows slope's 4 states. Rising lines yield positive slopes, falling lines yield negative slopes, horizontal lines yield 0 slope. Finally, vertical lines have 0 horizontal run. Dividing by 0 is impossible. The slope is undefined. Slope serves as the primary mathematical instruction set that dictates a line's fixed behavior across the coordinate plane. With slope clearly defined, we have the core component required to build an actual algebraic equation for a line. We substitute a known point, x1 and y1, and an arbitrary coordinate, x and y, into our slope formula. Multiplying both sides by the denominator gives the point slope form. Y minus y1 equals m times x minus x1. We can apply this immediately. If a line passes through the point 1, 4 with a slope of 2, we substitute those exact values in. This gives y minus 4 equals 2 times x minus 1. Distributing the 2 and adding 4 to both sides simplifies the equation down to y equals 2x plus 2. This structure is the slope-intercept form, written as y equals mx plus b. The variable b represents the y-intercept, the exact coordinate where the line crosses the vertical y-axis. The slope-intercept form is the standard for graphing because it instantly provides a specific visual starting point, b, and a clear trajectory, m. Despite how intuitive the slope-intercept form is, it contains a critical mathematical flaw. Watch what happens when modeling a vertical line. As the line reaches 90 degrees, its slope becomes undefined. The m value triggers a division by 0 error, and the format fails. To circumvent this, we use the general form, ax plus by plus c equals 0. A and b cannot both be 0. This resolves edge cases. Setting b to 0 removes the y term, leaving a clean vertical equation, like x equals 5. Conversely, for a perfectly horizontal line, we set a to 0. The x term disappears, leaving a stable equation, like y equals 3. If handed an equation in general form, like 2x minus 3y plus 6 equals 0, you can algebraically reverse engineer it back into slope-intercept form to check its steepness. Advanced engineering models require the general form. It provides a complete algebraic framework handling every geometric state without risking a division by 0 error. With an unbreakable algebraic framework in place, we can define complex spatial relationships between multiple lines without ever needing to draw them on a graph. Take the visual concept of parallel lines. This chart shows two parallel trajectories. For these lines to extend infinitely without ever intersecting, their geometric steepness must be absolutely identical. The algebraic constraint is simple. Two non-vertical lines are parallel if and only if their slopes are exactly equal. m1 equals m2. Now consider perpendicular lines, two lines intersecting at exactly 90 degrees. To translate that 90-degree intersection into algebra, the slope of the second line must become the exact negative reciprocal of the first line's slope. This generates a rigid mathematical absolute. The product of two perpendicular slopes will always equal exactly -1. We began by looking at a scatterplot of raw empirical engineering data, and we systematically built up a universal algebraic model to understand it. The concept of slope acts as the crucial bridge, connecting visual steepness to hard mathematical computation. While formats like y equals mx plus b provide quick visual intuition, the absolute architecture of the general form ensures that computers can map any line without encountering structural mathematical errors. By utilizing these foundational rules, engineers map accurate regression lines, predict material behavior under humidity, and define strict spatial relationships. Coordinate geometry provides the mechanism to observe the continuous physical world and translate it into a singular computable language.